Hey guys, welcome. So in this video, we're going to see that the idea of inverses in mathematics is thematic. So we're going to have a very broad discussion of what we mean by an inverse in mathematics. And for that, we're going to begin with a most general definition of what we mean by an inverse, and then look at several specific examples where we will see in the context of each specific example that the broad definition of an inverse retains the core meaning that it has. Yeah? Okay, all right. Now, let's get on with it. So if we want to be very, very broad, then the inverse is the yin to the yang, or it's the yang to the yin. And then symbolically, if we have some set from which we take little a or capital A, so I intentionally represented both little a and capital A because, like, if the set that we're talking about is a set of 2x2 matrices, then we're used to naming matrices with capital single letters. So capital A would be what we'd call that general 2x2 matrix, right? Okay. But yeah. In any case, if we have some set from which we take little a or capital A, and then there's a binary operation defined on the set called star, then we would symbolically represent the inverse of little a by little a to the minus 1 like this, and the inverse of capital A we represent by capital A to the minus 1. Now, a lot of students think that a to the minus 1 simply means 1 over a, and that's only true if the set is the set of rationals and the binary operation star is multiplication. So in general, a to the minus 1 means the inverse of a. Yeah? Okay. All right, cool. Now, this is what the inverse must abide by, because so far we're just like talking big picture what we mean by the yin and the yang. But this is what has to be true about little a and little a inverse, or capital A and capital A inverse, which is that when they interact with respect to the binary operation star, then they combine to make E, where E is the identity element for the binary operation star, and of course also considering the set, whichever set that we're talking about, right? Okay, so E is the identity element, and so the inverse of A is that which combines with A, so a to the minus 1 combines with a with respect to the binary operation to take the combination to the identity element. So that's what we mean by an inverse in the most broad sense. Now, if, like, the words that I'm using sound fancy and confusing, then it will make more sense when we look at the specific examples, which are to come soon. Now, again, E is the identity element with respect to the binary operation star on whatever given set we're discussing. Yeah, okay, so this is the most general definition of the inverse. And now on to the specific examples that I promised. So let's get on with the examples. So here goes, and I'm going to give you several examples. First, there ain't no such thing as subtraction or division. Why, you say? Well, now that we're empowered with this idea of the inverse, if we take star, the binary operation, to mean addition, and our set is the set of integers z, then notice that the inverse of a would be simply negative a, because when a combines with negative a with the binary operation plus, we would get 0, which is the identity element with respect to addition on the set of integers, right? 0 is that identity element, right? Okay, now, this is what I mean by no such thing as subtraction. Well, subtraction is just a short form for writing a plus negative a, right? So instead of a plus negative a, we write a minus a. And in general, subtraction is a short form for writing a plus a minus b. That is simply a minus b, right? Okay, but yeah, there's no such thing as subtraction. It's adding a negative number. Okay, so along those lines, no such thing as division, because we can see division as multiplying by the inverse of some number. So here, 1 over a is the inverse of a, and so when we multiply a by 1 over a, we get 1, and 1 is the identity element with respect to multiplication, right? And more generally, we can think of a times 1 over a as a divided by a, and it is in this sense that there's no such thing as division. It's simply the same thing as multiplying by the inverse of some number. For example, a divided by b is the same as a times 1 over b, where 1 over b is the inverse of some number b. Yeah? Okay, cool. All right, now, again, just to demonstrate that this definition of the inverse is very universal, let's consider the set of functions, polynomial functions specifically. Yeah, so for polynomial functions, we know that the identity element is x. It's f of x equals x, and here I've called it e of x, since we're going with e as being the identity, but it's normally like I of x equals x, or simply f of x equals x. That's the identity function, right? Because the binary operation is composition, little o, right? And if we take any function f and combine it to this x here, which is the identity element, then first, even though composition is typically not commutative, we could commute in this definition of the identity element, right? And or in this demonstration of the identity element. And so FOE or EOF, which are f of e of x or e of f of x, are both going to be f or f of x. Yeah, and so it's in this fashion that we demonstrate that e equals x, or e of x equals x, is the identity function. And so e here, or x, is playing the role that 0 plays with respect to addition and playing the role that 1 does with respect to multiplication. But obviously e equals x, or e of x equals x, is in the context of the binary operation composition, little o, right? Okay, cool. So then we know that the inverse function f inverse must have the following property, which is f inverse, which is the same as f inverse OF. Again, composition doesn't commute normally, but it does in this case when we're pairing f and its inverse. We can do it in either fashion, in this manner or in this manner. And what we should get, if f inverse is in fact the inverse of f, is that when these guys are composed, we should get x. And that's exactly how in algebra we defined the inverse, right? We said that the inverse function f inverse is that which has this being true, f of f inverse of x equaling x, or f inverse of f of x equaling x. Sorry, like I'm like laughing at my own English because like I don't script these, and so the syntax is kind of sometimes like bogus. But anyway, more examples, specifically just a couple, and then we'll wrap up. Now, again, I'm just trying to demonstrate how this definition of the inverse is very universal. So if what we're talking about is multiplication of matrices, so the binary operation star is matrix multiplication, then when we take A, an arbitrary 2 by 2 matrix here, and of course, we could do this for any n by n matrix, but let's demonstrate it with 2 by 2 matrices, then A inverse will have to be this. And I show why A inverse has to be this in a different video on linear algebra, so feel free to check that out, the inverse of a 2 by 2 matrix. Yeah, but yeah, when A is a 2 by 2 matrix here in maroon, then A inverse would be this, and you can multiply the two matrices and see that so long as star here is understood to mean matrix multiplication, A times A inverse is going to make I, where I is a 2 by 2 identity, and if you don't know what that is, that'd be this. And you can check that I is in fact the identity matrix. You can multiply A by I and see that you'll get A back, and yada yada, yeah? Okay, so our very final example is considering the set of integers mod n. So, set of integers, I should have written mod n here. This should be an n. My bad, guys. It's very rare that I put up with typos like this. I normally would re-record, but this video I like so far, so just forgive that. So set of integers mod n is what it should say, not z here. And of course, I've correctly displayed it here. So how do we fix that, y'all? So that I don't have to re-record this. I suppose we can do this. Yeah, and I could write n in place of it. I'm so sorry, guys. Normally this would really bother me, but okay, that'd do. So the set of integers mod n, that is this here, right? If we're considering that specifically, if we look at the set of integers mod 5, just to give a clear and specific example, I'll have a different video talking about an inverse in the context of integers mod n. But yeah, so they'll be like elaborating on this particular example in a different video. But yeah, if we just for now look at z mod 5, so the set of integers mod 5, then all of the elements that exist in the set of integers mod 5 are these guys. It's the congruence class of 0, congruence class of 1, 2, 3, or 4. Note what I'm saying is like the number 5 is the same as 0, so it falls in the congruence class of 0, mod 5, right? And so the number 10 would also fall and the congruence class of 0 mod 5, and so on. And the number 6 is the same as 1, right, mod 5, and therefore it falls, the number 6 falls in the congruence class of 1 mod 5, right? Anyway, in this context then, what we're doing is calling star the binary operation modular arithmetic. Well, modular addition is what it should be specifically, not just modular arithmetic. Modular arithmetic can mean multiplication mod n. But yeah, if we're talking that star is modular addition specifically, then this is what we'd have, which is mod 5. The inverse of 3 is 2, because 3 plus 2 would equal 5, but 5 is the same as 0, and clearly 0 or the congruence class of 0 is the identity element mod 5, right? Yeah? Okay, cool. All right, this is it for inverses. I hope like this allowed you to see why inverses are thematic, right? Like in mathematics. And yeah, they are like more broadly understood to mean all of these things in all these different contexts. Okay, all right, keep watching and take care.